Physical manufacturing transitioned from manual inspection to automated assembly lines to ensure precision at scale. AI governance is shifting, moving toward continuous and automated technical monitoring. Traditional risk assessments rely on static spreadsheets. These tools cannot account for the real-time fluidity and unpredictable outputs of generative models, which can change behavior with every new prompt or fine-tuning iteration. To bridge the gap between static legal reviews and high-speed deployment, developers are embedding risk scoring and bias detection tools directly into the CI/CD pipeline. This practice of integrating governance within the software development lifecycle defines the emerging discipline of AI GovOps. This new architecture replaces retrospective legal checks with programmable guardrails. These systems are designed to detect model drift and data bias in real time before the code reaches a production environment. This engineering shift is a direct response to the enforcement timelines of the world's first comprehensive algorithmic regulation, the EU AI Act. Modern AI compliance is a software engineering requirement. This pipeline represents a standard AI application. The EU AI Act uses a risk-based hierarchy, categorizing systems by their potential to cause harm. Minimal risk applications require only standard transparency. The provider adds a notice and the code runs without modification. That autonomy is restricted by the boundary defined in Article 6. This threshold separates consumer models from high-risk applications. When a model crosses this threshold, deployment pauses. The system undergoes a formal evaluation against safety and fundamental rights criteria. This classification dictates the entire development roadmap, determining whether a project requires a simple disclaimer or a multi-million-dollar compliance infrastructure. While Article 6 provides the criteria for risk, Annex 3 provides the definitive list of use cases that trigger the high-risk classification. The first two categories govern physical security, remote biometric identification, and the management of critical infrastructure like water, gas, and electrical grids. The next two control individual opportunity, including AI used for educational admissions and student grading, as well as employment systems for recruitment, promotion, and termination. The fifth category covers essential private and public services. This includes emergency response routing, the allocation of social benefits, and systems used to calculate personal credit scores. The final three categories involve state-level functions, predictive policing, migration and visa processing, and tools used by judicial authorities to interpret facts. These 8 categories govern the basic functions of daily life. The regulation focuses on these immediate utilities rather than hypothetical or long-term AI threats. Software operating within these 8 areas inherits the highest burden of technical proof required by international law. To see how these rules change a technical roadmap, consider a fintech startup building an automated lending platform. The startup's ingestion strategy involves alternative data. They pull from social media feeds, browsing history, and unstructured spending patterns to build a more comprehensive user profile. This data is fed into a proprietary large language model. The model is designed to find correlations between these diverse data points that traditional banking models might overlook. The output is a personalized credit score used to instantly approve or deny loan applications. Under standard DevOps principles, this architecture is efficient and ready for immediate scaling. However, building this pipeline without cross-referencing global regulatory frameworks creates a massive hidden liability. Organizations often assume that using a standard off-the-shelf foundation model limits their regulatory obligations to a basic privacy policy. The EU AI Act, however, evaluates the specific application of the output. Annex 3.5b specifically identifies AI systems used to evaluate the creditworthiness of natural persons as high risk. The use of social media and browsing habits further complicates the risk profile, as these inputs are high probability vectors for systemic bias and fundamental rights violations. The financial stakes are significant. Fines under the Act are calculated as a percentage of global annual revenue, creating multi-million-dollar liabilities for non-compliant systems. The startup is legally prohibited from launching the product in this streamlined state. The legal classification of the output has invalidated the original design, forcing a complete engineering redesign of the data pipeline. The high-risk designation requires the implementation of a quality management system, or QMS. This structural framework surrounds the model to strictly regulate all data inputs. The QMS programmatically enforces data governance. It tracks data lineage and ensures the use of synthetic data to preserve privacy during training and testing phases. The architecture must also include automated logging. A dedicated server must capture and store the model's metadata and decision-making history. This logging is a forensic requirement. Decision-making artifacts must be retained for at least 6 months to allow national authorities to audit the variables that led to a specific credit denial. High-risk systems also mandate active human-in-the-loop oversight. This creates a mandatory UI bottleneck. The algorithm cannot finalize the loan decision independently. It must route the recommendation to a human operator for validation. The final architecture is heavily fortified, prioritizing auditability and oversight over the speed of the original design. Compliance is achieved by modifying the structural logic of the data pipeline itself. These represent the two engineering realities created by the Act. On the left, a minimal-risk spam filter. On the right, a high-risk credit model. The minimal-risk pipeline maintains high deployment speeds by avoiding the friction of conformity assessments and continuous auditing. The high-risk pipeline operates under heavy technical constraints. Every outpoint must be logged, every decision must be auditable, and every final action must be validated by a human operator. Accurate classification is the most critical phase for any AI deployment. Technical governance requirements are established during the design phase. The market requires a new professional capacity, the ability to interpret the text of global regulations while maintaining the technical integrity of machine learning systems. The AI governance architect is the hybrid discipline designed to bridge the gap between regulatory policy and DevOps engineering. This role translates legal standards into programmable guardrails and automated workflows within the codebase. Mastering this intersection of policy and engineering allows organizations to adapt to the evolution of both AI models and international law. In a regulated environment, building a model is a common task. The ability to build a legally viable, high-risk system is a competitive advantage.